Yeah, we got a whole chapter on circles, ladies and gentlemen. It's a 9-section chapter. This thing's a beast. All right, we're going to start off with labeling some things. You may know what some of these are. You may not know what some of them are. Hence, why we will label these bad boys on that circle. All right, let's do this. So our center would be point C. Our radius, well, there's multiple radii in this picture. One of them would be, let's say, CE. Segment CE would be a radius. We also have BC and DC, if you were wondering. The order in which you label them, whether it's BC or CB, does not matter. All right, it's a segment, so you can reverse this bad boy. Diameter. A diameter goes all the way across and through the center, so that would be our BE. Segment BE would be our diameter. Okay, it goes through the center, and it goes from outside to outside of that circle. Okay, those should all be ones that you guys know. A chord you may not be familiar with. That would be something like BD. BD is a chord. Okay. An interior point means any point on the inside of the circle. C is the center, so it is an interior point. Why don't I label a point, let's say, F. That'll be fun, too, so we got a different one. Whoop, there we go. Let me just try that again. Okay, that's a better F. Okay, an exterior point, that'd be like that guy A that's floating out there. It's not on the inside of the circle. Again, I'm not going to ask you to label things like this on a quiz or a test, but I will use them in the context of a problem. I might reference a chord in the context of the problem, and if you don't know what the heck that is, you ain't going to know how the heck to do that problem. And that would be a problem. All right, again, some of these things you may already know. We're pretty familiar with circles, I'd say. The formula for the area of a circle is pi times my radius squared. The formula for the circumference of a circle, that's the distance around the circle. That would be 2 pi r, or pi times your diameter. Excellent. The circumference is to circle as what is to square or quadrilateral, whatever. That would be perimeter. That's just a way to remember it, okay? Again, not necessarily a test or quiz question, but a way to remember it so we can get familiar with it. So if I say this is the circumference, find the area, you know what the circumference is. You know which formula to use. All right, 2 or more coplanar circles with the same center are called concentric circles. Think about that as being like a bullseye. So I'd have a circle, and I'd have another circle, and they both have the same center. Okay, I could have 2, 3, 4, whatever circles that are concentric circles. So again, if I refer to something as concentric circles, you know what that looks like. All right, we'll talk about properties of those as we continue. All right, 2 circles that are congruent, or sorry, 2 circles are congruent if they have congruent radii. So if I have 2 circles with the same length radii, I know those circles are congruent. All right, a point is in the interior of a circle if its distance from the center is what than the radius? Less than the radius. And a point is on the exterior of a circle if the distance from the center is more than the radius. And a point is on the circle if its distance is equal to the radius. All right. Cool. That's fun. Exciting. All right, here we go. The circle. 10.1. Okay, let's do this. All right, as usual with any chapter, we got some formalities to cover. How would you measure the distance from the center O to the chord AB? Now, there's a lot of ways to get from the center to that chord. You know, I can go from here all the way to A, right? If my laser was on target, I go over this way or over to there or all the way over to B. But the way you would measure the distance so that you are consistent every single time is perpendicular to that chord. All right, that is the shortest distance. Short like Mr. Allen. Okay, so shortest distance to go from the center to that chord. That's how you measure the length, the distance it is from there. Alrighty, so if a segment is indeed the distance to the chord from the center, then it is perpendicular to the chord. It's just like saying if I'm like, hey, the distance is that segment, you know that it has that it's perpendicular. Okay. If a segment is perpendicular to the chord, then it is the distance to the chord. Okay? Again, this is just more of like if I say it's the distance, you know you have perpendicularity. If you've got perpendicularity, you know that it is the distance. Okay? All right, a little thinker here. True or false? Why or why not? The perpendicular bisector of a chord passes through the center of the circle, meaning if I am perpendicular to AB and I also bisect AB, will it pass through the center? And if you said yes, you betcha you are correct. The perpendicular bisector of AB does pass through the center. Okay? The distance is measured perpendicularly, right? If it's perpendicular to the chord and it passes through the center, then it is the distance, and it will split that segment AB, that chord AB, into two congruent pieces. All right, a lovely theorem here, the radius-chord theorem. If a radius is perpendicular to a chord, then it bisects the chord. So let's shorten that up. Radius perpendicular to chord, then bisects chord. Cool. The converse would be if a radius bisects the chord, radius bisects chord, then, let me keep it in the same format, my apologies, then perpendicular to the chord. Now, is that true? Well, let's see here. If it's a radius, it's going through it's from the center to the edge of the circle, right? And if it's perpendicular to the chord, then it bisects it. And then if it bisects that chord, meaning it splits it in two, it's going through the middle, then yes, absolutely, it shall be true. Let's visualize that for a sec. So if I've got myself, say, a chord right here, I send that radius through it, right? If it bisects it, it's going through the middle, and it'll be the shortest distance from center to that chord. So it's going to end up being perpendicular to each other. So these two this is reversible, right? Reverse. You can do the converse, and it will hold true. Heck yeah. So it'll be perpendicular, and if it's perpendicular, then it bisects, and if it's bisecting, then it's also perpendicular. All right, so those two are very, very useful. I could give you one piece of information, and you can then conclude the other. You smell that? It smells like proofs are coming. Oh my goodness, they're making a comeback. Don't call it a comeback. All right, you know what my favorite part about theorems is? Proving them. Oh, God, I love it. Don't just give me the information. I want to show you that it's also true, right? You guys love doing that kind of stuff. All right, so if a radius is perpendicular to a chord, then it also bisects the chord. All right, so we're proving the first part of the theorem. Now, you can do the converse. It's relatively similar, but we're just going to do this one. All right, so let's get a diagram going first. All right, so here's the situation we got here, the sitch, if you will. We've got a radius. It's perpendicular to a chord. So I'm just going to go ahead and, why don't we label these? Let's call it circle A. We'll make this point B, C, D, and we'll make that intersection E. So we're saying that AD is perpendicular to CB. Then it bisects the chord. So I want to prove that AD bisects CB. Okay, so let's think back. It's going to take a little bit to get back into proofs here, guys. We're just doing very minimal amount of proofs in this chapter, just a little bit, so don't be like, oh my God, they're back! No! There will be a few of them. We'll have some on some quizzes and all over assessments, but don't worry, not overwhelming like it was in first semester. Okay. So if something's perpendicular, I know I get a right angle. I'll just jot that in there right now. Now, if I want to prove that something's being bisected, I need to get, what, two congruent segments in this case. If I want to eventually get, and I'm going to jot that down in blue, I want to get these two congruent. If I can prove that CE is congruent to BE, then I can prove that AD is bisected CB, right? That makes sense. Okay, I like that. I like that. Well, how do I get congruent segments? Well, if you think all the way back to semester 1, if we got congruent triangles, we could get congruent segments through CPCTC, and away we go. Now, is there a way to prove these two? We don't even, wait, hold on. We don't even have triangles. Oh my goodness. If I've got a circle, drawing in radii is a wonderful decision. I'm going to draw in that guy. And oh my goodness, Mr. Allen, did you just create 2 triangles? Heck yeah, I did. Now, I've got a right angle, right? Pretty sure these are radii and they are congruent, aren't they? Because all radii are congruent. Woo-hoo-hoo-hoo! So I've got right angles. I've got, looks like these 2 hypotenuses, right, hypoteni, are congruent because they're radii. And may I be so bold as to say that AE is congruent to itself by reflexive property? I believe hypotenuse leg right angle would prove these 2 triangles congruent, thus getting me what I wanted, yes? Thus getting me what I wanted here. I like it. I get my congruent triangles. I get CE congruent to BE by CPCTC, and away we go with the bisecting. Let's write this bad boy up. All right, that'll give me some room to work here. Let's do it. We've got our, that wonderful statement reason chart. Brings back the most fond of memories. Love them. Man, I've missed you, proofs. I've missed you. I'm sure many of you are saying that as well. Alrighty, so let's see here. First off, we've got right angles, right? So I'm going to just say, actually, I'm going to go ahead and try and label these 1 and 2. Okay, is that cool with you guys? All right. You know what? You can't respond to me, so I don't care. It's cool with me. Angle 1 and angle 2 are right angles. Definition, perpendicular. That's how I knew that. All right, so I got my right angles. Before I forget, AE is congruent to itself by reflexive. Then I've got to draw AC and AB. You can do aux line or 2 points to terminal line, whatevs. And now I know that AC is congruent to AB. And why is that? All radii congruent. Do I have enough to prove these triangles congruent? Heck yeah. Triangle ACE. Ace. What you guys going to do on this test, right? You're going to ace it. And then ABE. Abe. Abraham Lincoln would ace this test. All right. And that was by hypotenuse leg, and some of us will also put the R there to remind ourselves that it's hypotenuse leg. Right angle. Got to have them right angles. All right. Why did I prove these triangles congruent? Well, I wanted to say that BE is congruent to CE. CP, CT, C. And then lastly, but not leastly, we've got our last step, AD bisects CB. And that is just by the definition of bisect. It splits into 2 congruent segments. Definition, bisect. Cool. That's it. I mean, it's an 8-step proof. It's got a bit to it, but overall pretty straightforward. We're getting congruent triangles to prove some segments congruent to get ourselves the bisecting. And like I said, the reverse of this goes, it's very similar, but yeah, man, that was fun. That was dope. All right, sometimes the formatting gets a little bit messed up in the transfer from PowerPoints to this program. So that's circle Q, not question mark Q. I've also got that PR is perpendicular to ST. Ooh, that's a lovely little piece of information. I'm just going to go ahead and jot in a right angle right there. And then I want to prove that PS is congruent to PT. Okay. All right. Well, let's see here. If I've got a let's see here, it's from the center, right? QR is drawn from the center. So essentially, if I were to extend QR through, it'd become a radius, right? So we'll go with that. Since it's drawn from the center and perpendicular to that chord there, it would also bisect that chord, right? That's the theorem we just proved. If a radius is perpendicular to a chord, then it will bisect the chord. And think of your radius as being drawn from the center, okay? We could extend it, it becomes a radius. Cool, we'll use it as such. So if it's perpendicular to and it bisects, that's a perpendicular bisector, right? This is one of the theorems that many of you struggled with early on. But if we have a perpendicular bisector, then any point on that perpendicular bisector is equidistant to the endpoints that it perpendicularly bisects. Meaning, since P would be on that perpendicular bisector of QR, PT is congruent to PS. Oh my goodness, this is a quick proof. I mean, we can pretty much jot that down right now, and you might be like, wait, what the heck just happened, Mr. Allen? Well, Mr. Allen and Finn are going to go through this right now with you, okay? So, first off, I know that QR bisects ST. And how do I know that? Radius perpendicular to chord, then bisects chord. Now, some of your teachers might be okay with you just saying Radius-chord theorem and abbreviating it that way. I like to write it out because it reminds me of what this thing actually means. So that helps me, and it's not like it's too long. So I like writing it out, but you know, whatever your teacher wants, then go with that. Okay. Okay, so I've got perpendicular and I've got bisecting. So I'm just going to say that QR perpendicularly bisects ST. And I'm going to write it as line QR so that it extends to P, right? Very subtle little nuance there, but that is true. Alrighty, so my reason for this is not the perpendicular bisector theorem. It's actually the definition of perpendicular bisector. Because perpendicular bisector definition just says it's perpendicular to and it bisects, which is what we have. The perpendicular bisector theorem and its converse are the ones where you have to have like congruent pairs of segments to get you one. We don't necessarily need that for this one because we've got perpendicular and we've got bisecting. All right, so if we've got a perpendicular bisector, then our proof is right there. PS is congruent to PT. And that would be our perpendicular bisector theorem. Yeah. Awesome. I love it. Fantastic. 4-step proof thanks to our new wonderful awesome theorem that we used in step 2. All right, no more proofs for today. We got a nice little just application type of a problem. Find the distance from the center of a circle to a chord 60 meters long if the diameter of the circle is 68 meters. Okay, well let's start by drawing this up. So I've got a circle, right? Ooh, you know what? Maybe I'll let's pop on a lovely circle here. I've got the fancy kind. Ooh, that's a nice circle right there. I just did that freehand. Alrighty, find the distance from the center. So let's pop the center on there. To a chord 60 meters long. So the chord is 60, right? And then, so I'll notate that out here, 60 meters. Okay, that's a wonderful M. Why don't I try that again? That's a little better. And then it says the diameter is 68, which would mean that my radius is half that, right? So 34. Now, we might be like, okay, well, this is what I'm trying to find right here, right? It's perpendicular to that. So I want to find just this portion. We'll call it X. That's what I'm looking for. Is there any other way you think I could use that radius of 34 meters in this problem? Well, I'm pretty sure that first off, my chord has been cut in half, so this is 30 right here. My radius can be drawn from the center to anywhere on the edge of the circle, and that's 34. 30 and 34. That certainly sounds like a triple-double to me. We've got ourselves an 8, 15, 17 triangle, so this guy's going to be 16 meters. 8, 15, 17, that's been doubled, or, of course, Pythagorean theorem works if you did not notice the triple. That's cool. So again, a strategy used for solving problems in geometry. Triangles, right triangles. Oh my goodness. Wonderful. Alrighty, if AB is the diameter of circle O, again, sorry guys, the question mark should be circle O, where A is negative 3, 5. So I'm just going to pop A over here, and we'll label that as negative 3, comma, negative 5. And B is 9, 15. This is our diameter, so I'm just going straight across through the center. Right there. Find the center and the radius of circle O. Alrighty, not question mark O. Well, how am I going to find the center? It's just the middle, right? So midpoint. Alrighty, so midpoint formula for my center of circle O. Well, negative 3 plus 9 over 2. That's 6 over 2, which equals 3. And then negative 5 and 15. Negative 5 plus 15 over 2. That's 10 over 2. That's 5. Alright. So I just found the midpoint. That's my center. So there we go. Now, to find my radius is just the distance from center to the edge of the circle, right? So I can find my distance between AO, or my distance between BO, or I could find my length of AB and divide that by 2. So I will leave that up to you guys. What I generally like to do, okay, that did not work well. What I generally like to do here in this kind of situation is I often just find my my diameter and then I divide it by 2. My reason for that is just in case I made a mistake finding my center, that doesn't affect the rest of the problem. You know what I mean? So I'll just go ahead and find AB. Square root, because this is the given information, right? This is what I know is true. So I'll do 9 minus negative 3. 9 minus negative 3, not 13. 3 squared plus, and then I've got 15 minus negative 5 squared. So that's 12 squared, which is square root of 144, plus, now that's 20 squared, which is 400. So that's square root of 544. And now I'm kind of regretting the not just doing the radius because this number is big. But with a quick little check, I can see that this can break down to 16 and 34, which would mean that I've got 4 root 34. That's my diameter, so my final answer is 2 root 34 for my radius. Okay, so I've got my center, I've got my radius, we're good to go. I just cut my diameter in half. All right, and, you know, and that could save you some time too, just because what if I just said what's the radius and I only gave you the diameter endpoints? Do you really want to go through the trouble of finding the center and then finding the distance? Just find the distance and divide it by 2. All right, so each one serves a purpose. Just use your own judgment and skills to figure it out. All right, last one here, guys. I know this video got a bit long. I do apologize for that, but I hope you thoroughly enjoyed the excitement of this video. So we got a circle, and it says the chord is 48. So I'm going to draw it over here, 48. And then what is the radius of the circle if the distance from the center to the chord is 7 meters? Ooh, a little bit of a change up. So that right there, this is 7. The whole thing is 48, so this is 24. Oh my goodness. If you remember your triples, piece of cake. 25 meters. Cool. Again, forming right triangles is a great way to work through your problems here in honors geometry. It's not every single time, but it's a great place to start. America, freedom, rock and roll, and Costco. And homework. Woo!